Hello viewers, welcome to Famous Julius Academy. In today's video, we shall be looking at the laws of Newton, Newton laws of motion. Um, we have three laws of motion stated by Isaac Newton. We shall be looking at the three of them and their application as well. So we start with the first law, which is also called the principle of inertia. The principle of inertia simply means the tendency of a body to remain at rest. So Newton's first law of motion states that every body will remain at rest or a uniform state of motion except an external force acting on the body. So now what does that mean? If a body is at rest, the body can only change its position when an external force acts on the body. That is Newton's first law of motion, which is also called the principle of inertia. So I'm going to write that here. The first law states that, or the first law states that a body will remain at rest. Everybody will remain at rest, except an external force acts on the body. So a body that is at rest will always remain at rest, except an external force acts on the body. So if a body is at rest, it will always remain at rest. So the tendency of a body to remain at rest is what we call inertia. So inertia is the tendency of a body to remain at rest. So Newton's first law of motion can also be called the law of inertia, which states that a body has the tendency to remain at rest, except an external force acts on it to change it. So that is Newton's first law of motion. And we have the second law of motion, which is very, very applicable. In fact, in every part of dynamics, we usually use it when we are dealing with the resolution of forces. When we are talking about the resultant force on the body, the second law is so applicable in this aspect. And what is the second law of motion? The second law of motion states that the rate of change of momentum is directly proportional to the applied force. He said the rate of change of momentum, the second law states that the rate of change of momentum is directly proportional to the applied force. So this is Newton's second law of motion. What did he state? He said the rate of change of momentum is directly proportional to the applied force. First of all, before you can understand second law of motion, according to Newton, you must understand what we call momentum. What is momentum? Momentum is a vector quantity that shows the relationship between mass and velocity. Now, the product of mass and velocity of the body is what we call momentum. The product of mass and velocity of the body. Now, if for example, I can compare, let's say I have two balls. If these two balls, this ball A and this ball B. Now, these two balls, they both have the same mass, m and n. But this one is moving with a velocity u, let's say a velocity of 20 meter per second, and this one is moving with a velocity of 40 meter per second. Now look at these two balls. They both have the same mass. If this is 5 kg, this one is 5 kg. But while they are rolling, this first ball here is moving with 20 meter per second, while this one is moving with 40 meter per second. So you notice that this one is moving faster than this. They both have similar masses. Now, this one has a higher momentum than this. Why is this one having a higher momentum than this? Because the product of the mass and the velocity is higher than this. So momentum, which is denoted as P, is equal to product of mass That is what we call momentum. So if, for example, let's assume that the mass of this first body is 5 kg, therefore the mass of the second body is also 5 kg. So these two guys are moving. Which of them will have a higher product of mass and velocity, which is what we call momentum. So for the first body, it's going to be mass is 5, velocity is 20. 5 times 20, that is going to give us 5 times 20 will give us 100. While this one is 5 times 40, that will give us 200. So if you notice here, this one has a higher momentum than this. This one has a higher momentum than this. So what's momentum? Momentum is actually the product of mass and velocity of a body. Now it does not necessarily mean that because the both mass is here, because the velocity of this guy is greater than the velocity of this guy, that makes the momentum of these two greater than this. No. If, let's consider for example, if I assume that the mass of this guy here is 5 kg, while the mass of this guy here is 2 kg, if I consider this one, its mass will be 2 kg, what will be the momentum? The momentum will be 2 times 40, which is 80. But if you come here, it will now be 5 times 20, which is 100. 100 is not higher than 80. So, momentum generally is the product of mass and velocity of a body. So it's dependent on the mass of the body and the velocity of a body. That is what we call momentum. Now, momentum has a unit. If you look at this now, we are multiplying mass and velocity together, and the unit for mass is kilogram times the unit of velocity is meter per second. It therefore means that the unit for momentum is kilogram meter per second. That is the unit of momentum. So in this case now, when I multiply 2 times 40, which gave me 80, I'm going to attach my unit, which is kilogram meter per second. Similarly, with this 200 kilogram meter per second, that is momentum. So this is the unit for momentum. So for us to understand using second law of motion, we said we must know what we call momentum. So the change of momentum. So if you say we have a change of momentum, that means to say we have an initial momentum, they will now have a final momentum. For there to be a change, something must be, one thing must turn into another thing. That's what we call change. It must be initial, it must be final. That's what we call change. So we have initial momentum, we have final momentum. So let's express this mathematically in an expression. So what are we going to have there? So the rate of change of momentum. What we use for the rates? Rates is, that is time. We are talking about time. So the rate of change of momentum, we're going to say change of momentum, change of P over T. This is what we call the rate. The rate of change of momentum. This is change of momentum. The rate of change of momentum is directly proportional to the applied force from that law. So the rate of change of momentum is directly proportional to the applied force. So we can put this, we can say F is directly proportional to change in P over T. Now from here, we can remove this sign of proportionality. We are going to have F is equal to, when I turn this into equal to, I'm going to introduce a constant, that's K, change in P over T. So, and from here, I can multiply this and this together. We have Ft is equal to K change in P. The value of K is 1, so we are going to have Ft is equal to change in P. So that's this. First times time equals to change in P. Both of them are equal to what we call impulse. So what is impulse? Impulse can either be the product of force and time or the change of momentum. That is what we call impulse. So what is the unit of impulse? The unit of impulse can either be, now here we say impulse can be equal to either force times time or change in momentum. Change in momentum. So impulse can be equal to force times time or change in momentum. Here, impulse, we can say what will be the unit of this impulse? Force is in Newton times time is in seconds. So Newton seconds is the unit for impulse. We can also say change in momentum We already know the unit of momentum, which is kilogram meter per seconds. But the actual unit for impulse is what? Newton seconds. Newton seconds. That is the unit for impulse. So impulse is the product of force and time, or the change of momentum. Now we are going to write it in a more open form. Momentum here, change in momentum. We already know what momentum is. We said momentum is product of mass and velocity. But because we are having a change there, it means that we have initial momentum and we also have the final momentum. That means the change will now be equal to the final minus the initial. So if we have that this momentum is product of mass and velocity, it means that the initial momentum will be mass times the initial velocity. This will be the initial. While the final is going to be mass times the final velocity. So the change is final minus initial. So the change in momentum is mv minus mu. So if we place that change with this guy here, we're going to have F is going to give us what is change in P? Change in P is what? mv minus mu over T. This is what we're going to have. And if you check very carefully, this is our Newton's second law of motion. But if you notice here, you notice that mass is common to both sides. So we can factorize mass. If we factorize mass, we are going to have F is equal to m bracket v minus u over t. If you recall the formula for acceleration, acceleration is the rate of change of velocity. The rate of change of velocity, that's acceleration. Acceleration is v over minus u over t. So if you look at it there, v minus u over t is what? A. So if I replace all this here with A, my equation will become F is equal to ma. That is the popular formula that you know. Force is equal to mass times acceleration. So that formula is from Newton's second law of motion. We state that the rate of change of momentum is directly proportional to the applied force. So what have we learned so far from Newton's second law of motion? First and foremost, we say that the law states that the rate of change of momentum is directly proportional to the applied force. We talked about momentum. What is momentum? Momentum is the product of mass and velocity. We talk about the unit of momentum. The unit of momentum is kilogram meter per second. How we get that? Mass is in kilogram, velocity is in meter per second. So we join them together, we are going to have kilogram meter per second. That's the unit for momentum. Then we talked about the impulse. When we cross multiply from here, we notice that we are going to have Ft is equal to k change p, where k is 1. So we now have Ft is equal to change p. And we say that impulse can either be product of force and time, or change in momentum. And that is what we call our impulse. And what is the unit of impulse? Force is Newton, time is in seconds. So Newton seconds, that's the unit for impulse. And what I'm seeing here, I notice impulse is Newton times seconds. What about work done? What is work done? Work done is the product of force times distance. Force times distance. Force times distance. Oh, that's one same unit. I thought it would be the same unit, but so impulse is force times time. Newton seconds. That's the unit for measuring impulse. And this is for second law of motion. Let's talk about the Newton third law of motion. So the Newton third law of motion. Newton third law of motion. Newton third law of motion. So what are the third law of motion states? The third law of motion is actually something that is universal. It states that for every action there is always an equal but opposite reaction. For every action, there is always equal but unequal and opposite reaction. This is actually something that is universal. If, for example, I decide to hit this wall, use my head to hit this wall, what will happen? I will feel the wall itself will also exert the same force on my head. And that force the wall will exert on my head is equal to the force exerted on the wall. Then me, I'm going to feel that force exerted on my head by the wall as a pain in my head. So that is it. For every action, there is always an equal but opposite reaction. The force I apply to the wall is similar to the same force that is applied to my head, equal in magnitude. The only difference is that they are opposite in direction. Similarly, when you are walking, you are having contact with the floor. The force your leg make with the ground is also equal to the force that the ground makes with your leg. So that is it. And this little table of information, we are going to look at three major applications of this guy. And three major applications are one. The first one is what we call recoil of a gun. Recoil of a gun. The second one we are going to look at is what we call rocket propulsion. And the last one we're going to look at is weight of the body. Weight of the body in a lift. So these are the three major we are going to look at, and there are formulas for each of them. If you are writing WAEC or NECO exams or JAM, and these are the three major applications you are going to be seeing under Newton table of motion. And sometimes they do give you calculation questions from this. The calculations are actually easy if you understand the principle that govern it. And all these I'm going to be explaining in this video. And the first there is what we call the recoil of a gun. When you are about to shoot a gun, that means you propel a bullet from the gun, what will happen is that the gun itself will jerk backward and before the bullet will move forward. So the force the gun uses to jerk backward is equal to the force that the bullet uses in moving out of the gun. So that is what we call opposite reactions. Opposite reactions and action. Action is you shooting a gun. Reaction. So the action is moving the gun moving backward, while the reaction is the bullet moving forward. And that is it. Now, if we are to shoot a gun, we say the gun will jerk backward with a particular velocity, and the bullet will move with a particular velocity. We are saying that the force that the gun uses to jerk backward is also equal to the force that the bullet uses in moving forward. So in this state, there is a conservation of momentum. That means the momentum of the gun is equal to the momentum of the bullet. The momentum of the gun is equal to the momentum of the bullet. The momentum of the gun equals to the momentum of the bullet, but they are just opposite in direction. So what will be the momentum of the gun? The momentum of the gun is going to be equal to the mass of the gun times the velocity of the gun, which is now equal to the mass of the bullet times the velocity of the bullet. So momentum is conserved, and that is the equation you can use in solving for the recoil velocity of a gun. If you are asked to calculate the recoil velocity of a gun, the recoil velocity of a gun is Vg. So if I want to look for Vg, the recoil velocity of a gun Vg is going to be equal to Np a Vb over mg. I'm making Vg sort of formula by dividing by mg. So this is the recoil velocity of a gun. That is for recoil velocity of a gun. Then we'll talk about the rocket propulsion. The rocket propulsion is also important because if you see a rocket moving forward, at the exhaust of the rocket, you always see some kind of fuel. That's the fuel, the gas usually expelled out of the nozzles of the rocket. So when that happens, the force at which these gases are expelled from the exhaust of the rocket is also equal to the force at which the rocket is using to move forward. Let's assume I'm drawing the rocket in this way. Don't mind my sketch. Don't mind my sketch. Let's just draw something with this nature. Let's say we have something like this, and this is the exhaust. So we have the fuel being, these are the fuel that is being used, moving out of the exhaust, and this fuel is the rate at which they are burning. The particular amounts of this fuel are burning at a particular rate. So the rate at which this fuel are burning is what called change in mass over T. So change in mass over T is the rate at which the mass is being consumed. And the force at which these gases are being released, the force is what we call thrust. The force is called thrust. So the force here at which they are moving out is called thrust. Thrust force. Thrust force. So we can denote that KT, the thrust force. So the thrust force is what is also equal to the force that the rocket is going to move forward. That's the thrust force. And these gases that are being expelled from the exhaust have a particular velocity that they are being expelled. You can call it that the velocity of the exhaust. So if we decide to multiply the change in mass over time and the velocity of the exhaust, both is going to give us a thrust force. So what the force that a rocket uses in moving forward, we call it the thrust force. The thrust force Ft is equal to the product of the rate of change of mass that is burning from the exhaust, the rate of change of mass that is burning from the exhaust times the velocity of the exhaust. That is the thrust force. So please take note of this formula. It is very, very important. So in the next video, I shall be seeing some calculations under this particular topic. And these formulas, we are going to be using them to resolve questions on this subject. And the last one we are going to be seeing there is weight of a body in a lift. We are going to see some different conditions of the weight of a body in a lift, and the three major ones we are going to be seeing in this video. And we are going to illustrate them here. So let's see the first one. Weight of the body in a lift. The weight of the body in a lift. So let's see the weight of the body in the lift. So in the weight of the body in the lift, the first condition we are going to check, let's say this is our lift, which is an absorption, and there's someone inside the lift, and the lift. Now we are going to analyze the forces in this lift. Remember, this person inside the lift is actually making a contact with the lift, right? So the weight of this body is going to come down. The weight is coming down. Then there is a normal reaction, which is always opposite to normal reaction. Is always perpendicular to the surface of contact at an angle of 90 degrees. Now, if its weight is not moving, it means that the upward force and the downward force are equal to each other. Or the sum of the forces acting on the body, or the sum of the forces in that system is equal to 0. So in this case now, you notice that we have three forces that are acting. So I can call it normal reaction. Let me just call it R. So if you notice, one is acting upward, one is acting downward, and this one is acting in positive y direction. This one is positive y direction. Y is negative y direction. Positive y direction is the normal reaction force, which is a positive force. While the negative y direction is the weight, which is minus W. If you do that, they are going to give you the resultant force, MA. And we notice that this lift here is not moving. Because this lift is not moving, the acceleration of this lift is equal to 0. So if the acceleration is equal to 0, m times 0 is going to give us 0. We're going to have r minus w is equal to 0. R equal to W. So that means to see the normal reaction is also equal to the weight, the body, which is all equal to mg. So that's the first case. The second case is when we have the lift, the body inside the lift, and the lift is moving upward with an acceleration of a. We also have our forces here. We have the weight W. We have normal reaction, which is R. Now, what is the resultant force here? We already know the resultant force that when this body is going upward, it tells you that when this body is going upward, the resultant force is acting upward. There is an acceleration that this lift is going upward. The resultant force is always in the upward direction. That is why it is going upward. So in this case, we are going to have R minus W is also equal to MA. So if we were to calculate this normal reaction force, which will also be the net force, so we are going to have R to be equal to MA plus W. Therefore, R is going to give us MA plus mg. So we can factorize m here. We are going to have m bracket A plus g. So this is it. That is for the second case. Why for the third case is when the body is moving downward. When the body is moving downward. So if we have this, we have our W, we have our normal reaction. Now our velocity is acting in this direction. The body is moving downward. In this case, what's the difference? The resultant force is acting downward. So it means that the downward force will be more than the upward force in this case. So we are going to see W minus R is equal to MA. So if I'm looking for R here, I'm going to take out this plus and bring this out. I'm going to have W minus MA is equal to R. So what is W there is mg minus MA is equal to R. From here, we're going to make him, if I factorize this, we're going to have m bracket g minus a is equal to R. So this is the third case. This is for the second case. This is for the first case. So watch out for these three. And in the next video, we shall be resolving questions on the first law, second law, third law of Newton. So please don't forget to watch the next video. Thank you for watching to the end. Please don't forget to like, to share, and to subscribe.